Afternoon. Oh, not quite yet. Top of the morning to everybody. My name is Tyler Peterson,
I'm Eric Cow.
I'm John McCall.
and our senior project was a modular smart wingsail.
So, as we all know, the majority of the Earth's surface is covered in water, actually roughly 70%, and only 5% of that has really been explored and discovered. And there's a reason for this. It's very expensive to do manned ocean monitoring. In terms of insurance costs for large vessels, crew salaries, and fuel costs, not only monetary costs, but also in terms of environmental costs of burning fossil fuels, ocean monitoring is just very expensive. So there's clearly a need for a cheaper, cleaner way to propel ocean vessels. And this has been addressed, a few ideas. Here we have some examples. This first one is actually from our own Professor Gabriel Elkheim. It's a PhD thesis. It's a fully autonomous sailing vessel. The second one is currently being developed by Teledyne. It's an unmanned surface vessel, also sail-driven. That can actually enter subsurface propulsion to avoid bad weather. This one on the very end is a concept for a tanker, basically a transport vessel, to use sails to be driven. And they all have in common sail power. And on top of that, they're all powered by Wingsail. So similar to an airplane wing, that creates lift to lift a vessel. We're mounting it vertically, and we're creating lift to move a vessel in the direction we want. So using these ideas, our goal was to develop a modular smart wingsail. So a sail that can be placed on an autonomous vessel and uses a low-power propulsion system, and also scalable to be used on larger vessels, as seen in the previous slide. And to do this, it has to be totally self-contained. So all the sensors and things it needs to set up the most optimum direction of propulsion, it's all on board. So this reduces the complexity and increases application.
So in order to achieve the goals that we specified earlier, we broke our design into 3 sections: the mechanical, the electrical, and the software aspects of our design. Our design process is highly linear in that each section would directly influence the parts that come after it, such as how our mechanical design of our wingsail would influence our sensor choice, and therefore it would influence the coding modules that we would need for our control system. An example of this would be how in our mechanical design we made our wingsail rotate freely about its mast, and therefore we would need a potentiometer on the mast itself in order to determine our position of the sail versus the vessel itself. This caused us to need a ADC module in our code, and also to implement an additional feedback source in our controller feedback design. An additional example of this sort of integration is seen in our user interface, where we took a rendering of our hardware sail and the data from our sensors and integrated it into a real-time display of the orientation of the sail itself. So the basic operating principles behind our sail is that the lift generated is a function of the angle alpha between the wind and the position of the sail. The angle alpha could be controlled by the tail flap and the tail wing on the end here. Therefore, it means that the magnitude and direction of the lift generated can be changed by adjusting the positions of the tail wing and the tail flap. Now, due to the physics of the design, it means that there's actually very little force on the tail flap and the tail wing itself. The wind provides the wind generates all the lift, and the wing actually just repositions itself accordingly. Therefore, our system is very low power, and the entire system is run off a 12-volt deep sea marine battery, as shown in our block diagram to the left. The inputs of our design, the inputs of our wingsail, are the data from our user interface, the potentiometer, where, as before I mentioned, it measures the position of the wingsail relative to the vessel, and IMU to measure the tilt of the wingsail, and an integrated wind sensor, which measures the wind speed and direction. All of this is fed into our AUAV3 aeronautical control system. The algorithms within the AUAV3 would then determine the optimal position for our wingsail in order to generate the lift needed, and it would actuate the flaps fusing servos to the position that we would need it to be.
So, due to the physics of the system and just to make the system modular, we need to develop a control system that takes in the data from the sensors that we've integrated and calculates what is the most optimal angle to produce lift in the bow direction of the vessel. So essentially, we need to maintain a angle of attack alpha that we desire for our lift, and we need to orient our flap angle here in order to give us a desired propulsion. The angle of attack alpha is what generates the lift, and then this flap is what increases the camber of the wing and increases the efficiency of the performance. So we take in wind and surrounding data, and we want to push the boat forward. So we need to generate a lift towards the bow direction here. What we use the tail for is to maintain this angle alpha. So it acts as a positioning system because since it's extended from the center of rotation of the sail, the tail creates a moment that sets the alpha angle. So what we do is we take in the data and we calculate the most optimal, and then pass it through a scaler, which is what the user uses. You put in a desired propulsion and a desired intensity, or a desired propulsion intensity. We then feed that into our feedback controller, which operates the tail wing, and then make sure that we're trying to maintain our angle alpha as the wind changes to keep us moving forward, or to set it without drag, basically set it in line with itself. We then also have to consider the fact that because we're using a sail, the lift that's generated, the force that's generated, is above the center of mass of the vessel. So the center of mass is near the surface of the water, but the force that we're putting is way over the top. So it's going to want to try to push the vessel itself over itself, basically wanting to capsize it. But the idea is that if we take the IMU, the inertial measurement unit that we have on board, we're able to limit the effect of capsizing by it's an autonomous controller that says if I'm going over too far, I need to let out my flaps and basically not produce as much lift. The current stage of our project is that we have a fully functional prototype. We have experimentally validated the physics of our system and the functionality of the system. We've done this by taking the wing and attaching it to a test bench, which is here, this mount. And we tested it in the wind, and then we used a pivot point here and load cells to calculate how much lift was being put onto the wing. Now, you can see here in this red squiggle line here, this is the actual load generated by the wing. The blue is what we expected we expected the wing to exert due to the calculations of the physics equations. And we can see that it's very close. They're very similar. They're near identical. And actually, the most important one we see here, this is the longitudinal direction. This is the second graph is the y-axis basically. This is the forward moving or reverse moving direction. And we can see how closely it matches itself. So it's very close. There's some disparity due to materials and drags that we didn't account for, but it validates our system. Additionally, we've taken the sail and we've actually put it on a vessel that we purchased. It's a cheap $150 7-foot sailboat. We'll show you a video of that just in a moment, but additionally, in the future, we would, actually next week, our compatriot Eric here has designed a RC-controlled rudder system. And what this allows us to do is when we're on the boat, or we can pull the person that's steering the boat, as you'll see in the video, we can pull them off, and we can put this remote control thing on there and show that the vessel can be manned without a person on there. It's not a fully autonomous system yet, but that's a whole new integrated system that we would have to start to design. That'd be a whole other senior project. So we'll go ahead and step into the video, and I'm sure you guys are all hungry and ready to go to lunch. But so if you have any questions, we're happy to answer them. But we will also be we are also going to be outside and ready to answer your questions there. We'll actually have the sail out there and momentarily. You can see it yourself. But here's a video. It should be playing. So this is just me laying down, and all I'm doing there is just steering the rudder. You can see here. So we're in this is Delaware Pond. It's down over by the old TI building. It's the off-campus facility for UCSC. And you can see I tried to turn there. I was trying to do a tack, but I had to go ahead and do another turnaround the opposite direction. There's some weird eddy winds over there, but you can see that we're actually moving, and we're able to sail the vessel just with this small sail.
And speed really isn't the name of the game. It's more just controllability and reliability. It's obviously pretty slow. These are lower winds. I mean, we're in a pond. We're in a
Less than 5
puddle.
miles an hour.
Yes, less than 5.
Yeah, actually the design, the physical airfoil shape comes from our professor Gabriel Elkheim from his PhD thesis. This is a symmetrical design, and it's actually calibrated to operate at winds around 8 knots. It's his most efficient wind speed. But we're happy to show this video to you later. We'll set up a monitor out there and we'll have some videos playing and have our sail there.
Any quick questions?
Any questions?
How fearful were you putting that in the water?
He's wearing a wetsuit.
We're in a wetsuit. There's no undertow in the pond, so that wasn't too bad. Actually, we were a little nervous at first because due to our budget constraints, we haven't made it fully waterproof at the moment. So if it goes over, not too good for us.
So again, the tail, so the wing is self-correcting. So for whatever position you decide you want to go, it optimizes, correct?
Yes.
To give you the forward.
Yes.
Forward,
Yeah.
motion.
We just basically set the throttle is set at full at this moment, and the wind's just controlling it. The wing is just fully autonomous. It's controlling itself and generating the lift. Any question back there, sir?
It could be if we had some sort of wind generator on board.
Oh,
Not a wind generator. Sorry, but like a
A charging
solar
unit.
power. Basically, yeah. So basically, what we figured is we could get a 100-watt solar panel that could fit easily on that boat
And recharge
fully
it.
power the system.
Yeah.
And currently, the energy calculations would suggest that we could run a full stall current on all 4 of our servos and our microcontroller run a full processor for 50 hours straight. It's a very low energy system.
And that's from a battery that's like this size.
Yeah, it doubles the ballast as well. And there's a nice counterweight on there that our Giant machine, and it's very precision. So it functions much better than we actually expected it to almost. Any other questions? We'd like to thank you guys all for coming. This is a big deal to us. We've spent a lot of time doing this. I'm sure all the groups feel the same way. And it's our pleasure to present to you today.